Yeah, welcome to discussion 6. I think today I'm going to try and not write on the board as much. I'm going to see if switching to screen sharing on a tablet works better, because I think I did that last time and it was a little bit better because the screen one was a little hard to read. So yeah, today we're going to be talking about Boolean logic and SDS and any other, I guess, random midterm questions that you might have. I think some of you were at the Saturday review session and that was really, really long. So if you have any questions from that, also feel free to let me know. Just to check in online, is the volume okay? Okay, cool beans. So I'm gonna assume that most people, okay, I'm seeing some more responses. It seems like generally people are feeling kind of iffy on state elements and timing and things like that, which is great because we're going to be doing a lot of that today. And for the midterm, yeah, dying is a very common place to be. If you have any questions or concerns or like specific questions, I'll stay behind a little bit to talk about that. But yeah, moving on. So today we're going to be covering kind of like Boolean logic and algebra first, which Sydney will be presenting on, and then we're going to be jumping into more of the timing stuff. As a quick overview, just to get everyone on the same page, we have a midterm on Thursday. Hopefully everyone knows that. It's going to be 7 to 9, and you'll be assigned a room and a seat unless you are approved for accommodations, in which case it might be a different time, an alternate time, or extended. There's also the option to opt for online if for whatever reason, like maybe you contract COVID or just some other things. So if you're in a situation, you can always fill it out from the exam logistics page on the website. It's going to be default in person, so you'll have to request for remote unless if you're a DSP student and your letter specifically says that, you'll have to do it through the DSP portal. The logistics are in, coincidentally, 911 post on Piazza. That was not planned, I swear. But it'll include all lectures up to the first part of last Thursday's lecture. So there were a few questions on what that actually entails. So it's basically everything up until the single cycle data path. So until the end of transistors. That being said, you'll notice like the midterm review didn't really have review on transistors, neither will this discussion section, and you'll find basically no questions about transistors on past exams, homeworks, labs, anything. And that's because it's a really new concept and it's not one that's going to be really tested. So I would just say like understand the general gist of transistors. You don't need to worry too much about like the whole semiconductor doping stuff. That's CE 16B kind of world. So it was mostly kind of introduced last semester as a way to kind of familiarize you with that. And then it kind of got expanded for an unknown reason this semester. So I wouldn't worry too much about it if you're like, I don't have any practice with that. Yeah, so yeah. So don't worry too much about that if all of it just kind of went whoosh. Yeah. So like the processes that's not in scope. That's the single cycle data path, and it will be on the final, and it'll be on project 3, but not the midterm. So for past midterms, excepting last semester, I believe, most of the midterms will include the data path. I would say summer 21, spring 21, and not fall. So the 2 early midterms last year, those all go up until data path for the midterm. I would just skip those questions when doing it because it was kind of broken up differently. And then fall 20 and spring 20 and everything before that, I think had 2 midterms. So you'll have to do 1 midterm and then like maybe half of a tail end of a second one, just because of the way that the class is split. And it'll be closed book, closed internet, closed person. You can have open handwritten notes, and so the digital resources, I believe, are the resource guides that you will get printed if you're in person, and if you're online, you'll be able to have it up on your screen. But for more complete logistics, it's on the website and it's in the pin post. And it will be proctored unless for whatever really extenuating circumstance you cannot be. That's a kind of separate process. Are there any questions about the midterm logistics stuff? Yeah. Calculators are not allowed, no. And same for online, no calculators, no compilers, no coding environments. Yeah. Oh yeah, something to note real quick. Something that we did notice in past semesters when things were online and when people had access to compilers and things like that, they would focus a lot on syntax and stuff like that. I would say like in person, online as well. Don't focus too hard on that. Like, oh, I don't remember exactly like how this instruction was written or something like that. That being said, like do write the correct one. But for example, if you forget like how to write like what the exact return value or like exactly what a C function was called or something like that, or if you forget a semicolon, it's not the end of the world. It'll be fine because it's all hand graded. So on the midterm, I would not spend your time worrying too much about like, is this exactly the correct syntax? Okay. If there are no more questions about exam logistics, we're going to move on to Boolean logic.
Oh, okay. So we're gonna start off today with some Boolean logic. So just some basics with the Boolean logic is that we use truth tables to represent input. Values on the left represent inputs, and values on the right tend to represent intermediate values or outputs. So sometimes you'll see columns like A, B, and then an intermediate column A and B, which can be used when you have multiple variables. And it describes all possible behaviors of a logic circuit. So in a little later slides, we'll see the logic gates. They're also presented in lecture. And what a truth table does is it allows you to see all the possible outputs given all the possible inputs. So for each input variable, that can take two values, true or false. So you have 2 to the how many variables, different combinations of true and false. And with a truth table, you can basically plug and chug into an equation and see what the output would be. And then when we're doing Boolean algebra, which works with equations, you'll see AB, which you know more familiarly as multiplication. That's A and B. And then A plus B is A or B. So we'll see an example of this in the next problem. And so some of the problems you'll have to do are to go from a truth table to an unsimplified Boolean expression, and this is known as a sum of products. So if you break down that sum of products sort of phrase, a sum is taking an OR of multiple expressions, and products will make up the terms, and those are ands. So we'll take a look at this in the next example problem. So this is from the spring 29 midterm 2. So here you're given a truth table with 4 variables, A, B, C, and D, and then you see the outputs. So if you take a quick glance at the table, you can see that in 4 rows, the output column outputs a 1. So the question is asking you to write a Boolean expression that represents this truth table using the sum of products. In this case, we don't need to simplify. So each row in the truth table where the out is 1 represents the product. That's an and term. For example, if you look at the first row where the out is 1, that would be if A is 0, B and C are 1, and then D is 0. So you can sort of think about how you would start to represent that in an equation form, where 0 is not of something and 1 represents something being true. The output is true if and only if any of these rows are true. So for example, this first row would be not A and B and C and not D. So in order for the output to be true in this case, you need all 4 of those variables to be in those states. Then we also have three more rows. This one is not A and B and C and D. You have A, not B, C, and not D, and A, not B, C, and D. So based on this, you can see that where a single variable is 1, you'll just use the variable itself, and where it's 0, you'll use the not of that. So each of those rows will be a product, and then in the end, to combine them, you will use the plus operator, which is the or, and that will be your final expression. So in order to get an output of 1, which is a final answer of true, you need either one of these 4 cases to be true. And that's why we use or, because we need only one of them can be true at a time, but you need one of them to be true for the whole logic to be true. So when you have one of those expressions, like you saw on the last slide, that's unsimplified, you can simplify them using Boolean logic. And the first note says you just stare at your expression and apply the simplification rules until they no longer can be applied. And that sounds a little confusing at first, but this table shows some of the common rules, and they are like normal algebra. So you have the commutative property for and or. So if you think of it like addition and multiplication, we have associative properties and commutative properties, and they are different for addition and subtraction versus multiplication. But this is just a list of some of the properties, the rules that you can apply. And it may seem a little confusing now, but you'll work through some of these problems in the discussion worksheet today. But when you're working on those problems, I would say have this chart up and available because these will really help with simplifying your expressions. So here are some of the logic gates. So I put some tips over on the side. There are basically three basic logic gates. You have and, or, and not. The not becomes a circle when used in combined in the other logic gates. But you start with those, and then you have and, or, and then not, and then nor, NAND, XOR, and XNOR. These can all be represented with their own truth tables, and you've seen some of these in lecture. And so there will be questions on the midterm or potentially the final where you have to go between logic gate diagrams, the expressions, and the truth tables, and it takes patience. Some of the problems you'll work through today take a little time to break down. But just some tips is when you're working with the equations, you want to simplify them as much as possible using the rules from the previous slide. And this will help you build a logic gate off of it or create a truth table. If you're given the truth table, use the sum of products to turn that into an equation. And then if you need to turn that into a logic gate diagram, you want to look at it left to right, where the most atomic expressions will be the earliest logic gates. And then as you go right, you'll start to combine those expressions. So this was a quick little overview. Does anyone have any questions? Yes. Yeah. Uh-huh.
Where they were able to to the not from A plus B to A.
Yeah, so are you talking about like the and form on the bottom?
The or form.
Or the or form?
Yeah, they just moved the bar on top of A plus B to on top of not A, not B.
You mean like keeping the or?
No, they just moved this over here and said it worked.
Oh, so yeah, you don't have to separate the knots like above each of the gates, just kind of makes it a little clearer. Because it's or actually
They have the long bar and then like underneath that were the two short bars.
oh gotcha. Yeah, so that I believe that's not De Morgan's law. It's probably a simplification of a different circuit because De Morgan's it kind of like distributes inside, so you wouldn't keep the external like big knot or overall bar. So do you remember which lecture it was?
I can ask that.
Yeah, sure. So we're working on questions later. I'll just pull it up. Does that sound okay? Okay. Oh yeah. Okay. Yeah. So well, I can't remember. So what it was one large bar over the top, and that was equal to small bar over A and small bar over. And then so as you kind of go through, what you're able to do is basically, if the left side had no knot at the very top, then it would be reversed on the right. So that's why it happens as well. Actually,
I'll just write it on the board.
What question?
here. Which slide was that? Here, I'll just share my screen. Which slides? Yeah, they're posted in just the resources drive. It's linked in the central resources post. Yeah. Sorry, which slide was it again?
I think it's like at the very bottom.
Okay. Okay. Yeah, so the confusion was here. So basically it's kind of going through different examples of how De Morgan's law might work. So like for this one we see on the left, it's like, oh, not, and then the whole of A or B. And so based on De Morgan's law, so you switch the operator and then you separate out the two ors, so or separate out the two nots. So it's not A and then and not B. And then when we look at like, oh, what if we want to apply De Morgan's law to something that doesn't have a knot on top? Then in that case, like it's the opposite of what's up here. So you want to negate the whole thing. So as opposed to having just, oh, not A and not B, then you would have not in parentheses and then not A and not B. So it's kind of like, because this doesn't have the overarching knot over here, and then this has the overarching knot and then this one doesn't. If you get rid of it on this side, then the opposite is kind of applied over here. Does that kind of make sense logically? So if we kind of tried to simplify this, it would be, let me see if I can annotate. Maybe that'll help. So like this one would look something along the lines of like, so not A or B is equal to not A and not B. And then whereas, say if we had this one, we would say, okay, we have A or B. Oh. Okay, yeah, it's on Zoom. Oops, I guess that didn't realize it didn't actually present up there. Maybe what I can do is I don't actually know how to get that to transfer. Okay. Okay, that doesn't actually work, I guess. Let me see. Let me see if I share my entire screen, if that'll help, actually. Yeah. I'm just gonna share my entire screen. So 275. Okay, so if I now annotate, will you be able to see it? Yeah, okay, cool, this works. So yeah, what we had before was, okay, so we had not A or B. Yes, you guys can see that now, right? Okay, and that becomes not A and not B separately. Whereas if we say have something like this, so we have A or B initially, then we want to make sure like the whole negation thing is kind of applied here. So what this is equal to is not A or B, right? So because we want the knots to cancel out. So if it's if we have one knot kind of going on, we need another knot to kind of cancel out that knot, right? Because if you do two knots, then it's going to effectively look like it wasn't there at all. Does that make sense? So it's kind of like if you negate something, like for example, if you have 3, it's negative 3, right? So it's kind of the same concept as that. So then if we try to apply De Morgan's law to this, then what we would do would be, okay, so not A or B is going to be equal. So we need to apply De Morgan's law to inside first, because we always do inside out. And from our previous kind of line, we can see, okay, well, we have not A or B, so that's going to be equal to not A and not B. Oops. And so what that would look like in terms of drawing it out like this would be, okay, small bar over A and small bar over B, and then big bar over both of them. Does that make sense? Why? Okay, I'm gonna need either small knots or confused. Okay, cool. So yeah, that's why kind of that major bar exists over there. And the same kind of concept exists here. So I'm guessing this is what was confusing because it just more letters got introduced. And so if we want to break this down into what on the right hand side it is. So over here we can be like, okay, well, A we know that we want it to be like some complicated form of not. So what would happen here is like, okay, well, we have A and B here. A and B, or C and D. And so we want to be able to negate the whole thing to be twice to be able to get this equation. So let me expand this a little. So it's going to be, again, like what we had before. So not, I should use different brackets. Let's do this. So not, let's, okay, instead, there we go. A and B, or C and D. So we have one bracket here, so that's negating the whole thing, and then this is negating the whole thing again. So far, does that make sense? So it's the same concept as before, it's just we have A and B as one kind of major thing. I also realized we are able to see everything now. Sorry about that. What does the negations accomplish? Isn't the right more simplified? So the right-hand side is not more simplified. The right-hand side is actually very, very complicated. It's kind of to show like how you might reach that point, because oftentimes you'll get an equation like on the right-hand side and you want to be able to simplify it. So being able to go from a more simplified form and reason out why a more complex form is pretty useful as well. Yeah, so you might get prove these two equivalent, or are they equivalent, or like write this kind of circuit. So you might like see a circuit gate or a set of gates and then be like, okay, write out the most simplified Boolean expression for this. And so we can go through an example of that later. Oh yeah, Maddie and Sydney, I realized because I'm broadcasting my whole screen, I can't actually look at the messages. So okay, I have, I think, so online, can you message, can you message either Sydney or Maddie your question? Because I don't want, if it's a private message, I don't want to broadcast it for the entire room. Sorry, I'm not sure who exactly it is, but also I'm going to spotlight myself. I just realized that might be more useful. There we go. Okay. So yeah, once we have this, then okay, it's just kind of a similar process to before. So we have, okay, so not, and then we want to be able to distribute it. So we're distributing this not into the A and B part, and then or C or D part, and we're viewing everything in the parentheses as like one mega kind of chunk. So that's why this bar exists across both of them. Oopsies. I can't edit that now. There we go. Okay, so then we distribute this, so we get not, and then A and B, so that's one mega thing, and then we want to make sure we follow De Morgan's law here. So we want to switch this to and then we'll have not C and D. So that's what results in the right-hand side. If we wanted to go one step more complicated, then we could just distribute this negation inside to A and B, and then C and D as well. And then so we would get like further, even littler sub bars. Are there any questions how we got there? So no, so for this one, usually you want to either go from left to right or right to left. And on exams, like they'll tell you like either prove these two are equivalent, so you can go from either side to see which one's easier to go to, or they'll tell you, oh, simplify this expression. So usually they'll never tell you and say create the most complex circuit possible, because you can have infinitely complex circuits. So it's usually towards the simplification side. But sometimes, like if you want to prove that the two sides are equal, some people find it easier to go from simple to the hard, more complex one, and some people find it easier to go the other way around. Are there any questions how we got here and why there's one bar over top and why it's not exactly the same as what we saw before? Okay. In that case, then we're going to go back. So I will take a screenshot of this and put it on the slides as like kind of transitions. So you'll have it later as well. But I'm going to move back to the slides for now. I also realize I need to clear the annotations because this doesn't actually work like this. Yay, Zoom. Okay. Cool beans. I think I can go back to sharing just this, just broadcasting this one now. So I'm going to share a window instead. There we go. Okay, we should go back to being able to DM without showing everything. But yeah, some of these kind of properties. Do we want to go over the properties and why they're the case, or feeling okay on that? Good. Okay. Yeah, so I would just advise put a screenshot or just copy it onto your cheat sheet, because you're not required to kind of memorize everything, but it's good to have the practice. So when you're going through practice exams, try not to look at the table when you're doing it, but have it on hand, like if you really can't remember something, because it makes converting and simplifying a lot easier when you're able to recognize like, oh, this looks kind of similar to this particular rule. So yeah. Okay. So there are some questions on the worksheet that are related to Boolean logic. So I'm going to skip the pre-check for now, but we're going to go to 2.2 on the worksheet, and there's 4 subparts. So I'm going to give maybe 6 minutes to work through them, as many of them as you can, and we'll walk through them together in a moment. Okay, cool. So in the interest of time, we're gonna go over the answers and the process by which you can approach each of these. Let me make sure I'm. Okay. I think I'm screen sharing the correct thing. Let me. Okay. Wait. Nope. Okay, online seems to have it. Let me reconnect. Okay. Cool beans. So we're gonna start going over the answers to this now. So just in the interest of time, we're gonna skip over 2.1 for right now, but we can go over it later if we have more time at the end. But yeah, so starting from kind of 2.2 part A, the point of this question is basically to look at different types of problems that you might have and figure out what's the most efficient way basically to approach it. So kind of starting from the first one, what we have is, okay, well, we see that we have A plus B and then A plus, or A or not B, and A or sorry, A or B, or and A or not B. And then we end that with a C at the end. So something that you might want to take a look at when you have that is notice that, like, okay, we have both A and A right here. So we might want to do something with that. So by the opposite of the distributive, yeah, there we go. Distributive property, we could do things in reverse, for example. So this could equal something along the lines of, say, A and then plus B and not B, and then and this all with a C. So this is by the distributive property. And then once we have that, then we notice, okay, well, these two are the same kind of letters or the same input. And so we might be able to do something with that. So when we take a look at our chart, what we have here is, okay, well, let's see. If we have a certain input ANDed with another input, then the output is automatically going to be 0 always. Whereas if we have a certain input ORed with the negation of that input, it's always going to be 1. And the reason for this is because when we have the inverse, we know that for ANDs, we need both inputs or all inputs to be 1 in order to output a 1. So even if one of them is a 0, then we're going to output a 0. So if we have an input that has 2 possible values, regardless, so say if A is equal to 0, then not A is going to be equal to 1. But if we AND those together, it's going to turn out to be 0. And whereas like vice versa, if A is 1, then not A is going to be 0. So either way, it's always going to be 0. But the opposite is true for OR, because we have an OR, and OR only needs one of the values to be 1 in order for the output to be 1. So we can guarantee that between A and not A, one of those values is always going to be 1. So our output overall is going to be 1. Does that make sense why? Okay, so in this case, we have a B and not B, and so this is going to give us a 0. So eventually what we're going to have is, okay, we have A ORed with a 0, and that's ANDed with a C, and A ORed with a 0 is always going to be A because it's relying on whatever value is there, because the 0 is not really going to matter in an OR. So we can really kind of stop thinking about that. So this is going to be inverse. And then we're going to result in an A and C answer for this one. Are there any questions as to how we got there? Okay, so then moving on to the next one, you can see it's significantly longer, but we kind of follow the same general principles. So as a guiding principle, like when we're looking at these things, we want to try to identify what's the same or what can we break down. So right here we can see, okay, well, let's try to kind of highlight what values might be the same across all of this. And so we notice that, like, okay, well, we have all of these that have like a bunch of ands and or stuff like that. So we can try and pair them up. So for this one, we can see, okay, we have an A and C right here, so that corresponds correctly. For this one, we have an A and then not C, and then A and not C. And then for the first one, we can see we have a not A, not C, and then not A and not C. So somehow those might end up being pairs. So if we go back and look at our chart, something that we do notice is that if we have the same thing kind of same thing in the front, we can take it out and then OR it with whatever is different right here. So if we take a look at that in comparison to what we have at the bottom, we can apply it. So the A, for the first one, if we have not A, not C, we can consider that as a whole. And so we can pull out not A and not C and then deal with the B and then not B separately. So what that's going to wind up being is, let's see. So yes, so it's going to be something along the lines of this. It's going to be the OR form, because we can see the result is a distributed version and not like a clumped together version, and that's what we're trying to get to. So let's try to pull that out. So, okay, so it's going to pull out the similar thing and then OR the two things that are different. So for the first one, what we can do is I'm gonna pull out not A and then not C separately because we haven't applied De Morgan's law, and then inside we have not B or B. Similarly, we can do that with the second one. So we're going to have A and then not C, and then pull out B, or not B and B, or B and not B rather, if we're to go in order. Oopsies. So B and not B. And then for the third one, what we have is A and C, and then we're going to be B or not B. So from the earlier, so this is going to be distributive or. So from the previous example, we remember that not B or B, so not input or input, what's that going to equal? 1, okay. So that's going to be 1, and this is going to be 1, and this is going to be 1 as well. So then if we kind of take that at the bottom, well, if we're ANDing something with a 1, we don't really care about the 1 part because that's always going to be an input, so we care about what's at the front. So that's going to simplify out to be not C, not A, not C, and then or A and then not C, and then or A and C. So now we want to apply the same rules of what we saw earlier. So this is identity, or not identity, sorry, inverse. Now we want to kind of apply the same rules that we saw at the beginning. So now we want to identify what's the same and what's different and what can we pull out, because we can see that we have a lot of similar letters, so we want to try to simplify that more. So let's use a different color. Let's use orange. So we can see that A and then, or sorry, not C and then not C here correspond. And then we can also see that A and then A here correspond, but we only have one of these values, so it can only go either over here or over here. So that kind of presents a bit of a dilemma, but luckily because this is hardware, we can actually manipulate it to be what we want. So if we, like, for example, say, okay, well, we already have an input 1, And then we want to maybe like OR it with another one. Would that change the output? So similarly, okay, if we have an input A, and then we're going to just OR another input A from like the same area, is that going to change the output? No, right? So if we just kind of OR the same kind of input at the same level, again, it's not actually going to change anything. So we're going to kind of give ourselves an extra input right here. So we're going to add a cheeky little input right here and do A and then not C. So we're going to give ourselves an extra one. So instead of this corresponding, we're going to make this correspond instead. So now we can see that we have kind of pairings going on separately. So now they can kind of, I use the word dissociate, that's not really the right word, but they can like kind of segregate to their own pairings. So now if we go on to the next step, what we can see is, okay, well, we can pull, if we go back to the original part, this is kind of starting to look a bit like this equation, right? So we can pull out the similar item and then and the two that are not similar. Oops. And so if we take a look at that, what that would result in here is because C is not C is similar. So we're going to pull out not C, and then we're going to OR it with, I think, is it the other way around? Nope. Okay, we're good. So we're going to OR it with A and not A. And similarly for the second one, we're going to do the same thing, but with A being pulled out. So we pull out A and then we're going to OR it with C and not C. And remember from earlier, not input and with an input is going to be 0. So this will be 0, this will be 0. So effectively they don't matter because we have a series of ORs. And so our final output is just going to be equal to A or not C. This one? Yeah, for sure. So let's say like we have some kind of like input right here. So we have, let's say we have an and, we have an or right here. Oh, that's gorgeous. Okay, let's try that again. Okay, let's make it slightly more, that's not that much better, whatever. Let's say we have like two inputs here, some kind of output, two inputs here, some kind of output. Maybe this goes to a giant and then there's some kind of output on B here, or let's do just output. And we have A, B, C, D. So this is going to have some kind of output, and then this is going to have some kind of output right, as well, right? So say if we just attached another input right here and then made it A and B. What's this output going to be equal to? This one, right? Yeah, so these two are going to be these two are going to be equivalent. So if we have two like equivalent inputs into some kind of gate, is that going to change the output? Because we just, right, so because we just repeat the input twice. It's kind of like being like, okay, well, we're going to pass in 0 twice, maybe a 1 here, or we're going to pass in 1 twice and then a 1 here. So it's just repeated. So we can just attach the same thing onto as an input at the same level without worrying that it'll change the output because we're outputting the same value. So that being said, this will not work for everything in Boolean logic because, like, for example, if we for example, have an XOR, that might not work because multiple input XORs are going to basically count how many ones outputted or how many ones as inputs that you have and how many zeros that you have as input. So if you have an odd number of ones, it's going to output a 1. If you have an even number of ones, it's going to output a 0. So say if we had, say this is XOR, if we added another input right here, it's going to change the output because we count how many inputs there are. Does that make sense? Okay. Are there any other questions for A and B and how we got there? Okay. I'll really quickly, I think, between C and D. Okay. Yeah. I'm going to move on just because I think SDS was the heavier part. I'm going to just briefly go through. Okay, wait, actually, I'll leave maybe C and D towards the end if we have time for that. So we have logic gates as well. That's just kind of recognizing which ones are which. So like the triangle ones are knots, the one with the kind of solid edge, and then the cone shape is an and. The one that kind of looks like a weird tulip thingy is going to be an OR, and then the double line is an XOR. And then if it has the little kind of nubbin at the top, that's going to be considered not. You have a question? Part B is A or not C. I'll come back and solve through C and D later if we have time. But if you have questions about that, feel free to say after. Okay, so we're going to jump into the state intro part, and we have, I'm going to go through the slides just really quickly because they are the same ones as we had for the review session. So let's see. I do realize also now I have to reselect which window to share. Yay, okay, cool. So we're gonna just jump into SDS. I'm gonna briefly review some terms and generally how to look at things, and then we're gonna jump into some examples because SDS is something I think best learned through examples. So just to review, just as I guess kind of thumbs up, medium down, how do we feel about definitions and the equations? Good, medium. See some good, some kind of meh. Okay, yeah, we'll go through them a little bit. Sorry if you are familiar with them. A little bit of review won't hurt. So yeah, just kind of to get started, we have our clock, which is the central timing system of the entire synchronous digital system, or SDS. And there's only one clock per system. And the reason for that is because we want our hardware to be synchronized. There's probably some example out there where like different hardware components like aren't synchronized, and that's just beyond the scope of this, but I'm sure there's always an exception because there's always an exception to everything. With that being said, it doesn't mean that all timed units will be looking at the same clock or clock input all the time. So what does that mean? Well, the clock input, like it's just a kind of square wave. In reality, it's more of like a kind of curvy and then to straight wave, but we're gonna just look at it as a square wave. And so it's gonna go low to high to low in a very regular pattern. And this is also because it's just a 0 or 1, it can also be negated, it can be manipulated. So an output from a clock can be split into say like multiple directions, and then maybe one of the options it'll be knotted, so then be inverse, and we'll see that in an example in a second on the worksheet. So a state element is something that is clocked, and this means that it will have persistence. Basically, it's going to be written to according to the clock cycle, and it'll also be overwritten according to the clock cycle. So this is things like flip-flops and registers, which we'll talk about in a second. It's very different from things that we were looking at earlier, so like logic units and things like that, because those, whenever the values pass through, it just kind of forgets about them. It doesn't even realize that anything has happened. And even though those items do have a delay, because we talk about like, oh, the AND gate delay, the NOR gate delay, just because they have a delay doesn't mean that they remember the value during the period of that delay. It just means that's how long it takes for the value to pass through and be like manipulated however it needs to be done. State elements are also always going to have that little triangle. So if you look at any register, you'll see that like there'll be the regular box, there'll be the D for the data input and the Q for the output. And then you'll see at the bottom, maybe right-hand corner, maybe the entire bottom, there'll be like a little triangle, and that will always represent something that's clocked. So when we like look at the data path stuff next week, you'll notice that in the data path, certain items will have like that little triangle symbol and certain ones will not. So a logic element is an unclocked element. These are things like Boolean gates, and we also call them as like combinatorial logic, which we will abbreviate to be like CL later, just because it's a really long name to say. And these don't have persistence. They don't remember anything. You can just think of them as like a wire that somehow like has values that take a while to pass through it. So we'll skip that for now. And then flip-flops, or FF, is a state element that stores only 1 bit's worth of value. So registers we know store 32 bits, flip-flops only store 1 bit. But registers, we have 32-bit registers. Registers can basically be any size because they're kind of just end flip-flops kind of chained together. You don't have to worry about how they're chained. But if we think about like at the transistor level, like they're basically like a set of wires and things like that. And so can basically think about it like different flip-flops that are chained together will affect each other. Are there any questions so far? Yes? Yes, we'll talk about that on the next slide, but yeah, there are a lot of different names for things. So, okay, Speaking of timing and critical path and things like that, so right here at the very top, we can see it's a pretty nice square wave, and this is going to be our clock. So we can see that it goes from low to high. We don't know really what values, we just think about it as 0 and 1. So the rising clock edge is the period of time that basically the value is going from 0 to 1. So that's represented by the pink right here. And the falling clock edge is the opposite. So it's going from 1 to 0 right here. So in 61C, almost always will, for everything that's being timed, we look at the rising clock edge. And you'll usually be told like, oh, don't worry about the falling clock edge. We don't time anything according to that. And yeah, you won't calculate anything like that, but it does get mentioned because if you've maybe like looked at past exams or like that, you'll notice that, like, for example, when we write to, when we're in the data path, we'll write to the register file sometimes, or write to registers, we'll read from them, and we'll talk about this in the upcoming lectures, next 2 lectures. But sometimes like you won't be able to access things at the same time. So sometimes you'll be able to time in accordance to the falling clock edge as well. Like maybe on the rising clock edge we read, and the falling clock edge we write. You don't have to worry about how that works. It's just like, that's why it's important, and it actually does come into play later on. You don't have to worry about it for the midterm though. The setup time is the amount of time before the rising clock edge for which the input or the signal must stay stable. So this means that during this kind of dash dot line to the kind of pink oval thing, the input must be a straight line, and it can't curve or bend or change in any way. The opposite of that is the hold time. So it's the amount of time after the rising clock edge that the input must stay stable. And that's represented by this dotted line. So in between these 2 lines, the input must be a straight line. The clock to Q time, sometimes abbreviated as CLK-2-Q or C2Q, is the amount of time after the rising clock edge that it takes for the output to be able to be sampled from the Q. So this is represented as the dashed line right here. And it is always the case that the dashed line is either going to be the same as the dotted line or after it. And so that means the clock to Q time is going to be always greater than or equal to the hold time. The reason for that is because if we don't have that, for example, we know that by the kind of dashed line, we can sample from the output and know that the value is going to be completely written already. However, if that dashed line is before the dotted line, we can't actually make that guarantee, because between, oh, I can use my mouse, I forgot I don't have to hit that thing. Yes, so between this line and this line is when the values are being written to the register or the flip-flop or whatever you're writing to. And so we can only guarantee that everything will be set after the hold time. So if the clock to Q time kind of occurs before that and we're trying to sample it, then it kind of violates that hold time, because then it's like, well, I'm sampling before you're done writing, but so we can't make any guarantees. Yes?
So if they're asking for like the value,
Here? Would it be what?
like unknown behavior, or would it stay at 0?
That's a great question. Between these 2, actually, you'll have the value may change. It's just that the input doesn't have to change, because like think about it as like, okay, so between the setup time and hold time, the input cannot change. We don't know, and we don't care really what's on the output, because we don't know the behavior on the output. We just know that the input, it's going to be consistently written. So after this point, we know that the input can change, but we can't guarantee anything about the output until the clock to Q. So this is still, yes, indeterminate or undetermined behavior.
Like on the graphs.
Yeah, so if something like, for example, you're trying to read in between value between here, then yes, it would be scribbled back, and we'll see, we'll do some examples of that later. Okay, so we're gonna go through a real quick example of just identifying what's okay and what's not okay for an input. So we're gonna look at a couple of inputs. Okay. Oh, I forgot that I had that. But yeah, basically the hold time, clock to Q, and setup time kind of propagate to the rest of the clock as well. So here we have an example of just some random input. We don't care about what. Does it violate any of the timing conventions? Give you all about 20 to 30 seconds to think about that. Who thinks it does violate some time convention? Who thinks it doesn't? Who's not sure? Okay, yeah, so I guess it's pretty optimistic that no one said that, yeah, it does violate some stuff, because the main thing to pay attention to inputs is where they're changing, because we don't really care about like where they're stable, because like they're stable, so they won't violate anything. So we care about, so this change from low to high, and then this change from high to low. So going from this one first, we see that it changes between the hold time and the clock to Q time. So this is, remember, the input. We're not sampling anything. So if the input changes after the hold time, but before the clock to Q time, that's totally okay, because we have no guarantee. We have nothing that says it can't change before the clock to Q time. And because we know, at least in our setup right now, that values are only written to registers based off of the rising clock edge, we don't have to be worried about like, oh, what if like something changes here or whatever, like we'll like override the value of the register or something like that, because it'll only be kind of at the next kind of clock cycle that values will start to be written again. So even if you change here, if you change like right before the setup time right here, it's not going to have recognized this section as having done anything at all. Does that make sense? Okay, so then looking at the second one, we can see that the value changes here as well, but this changes well after the clock to Q and well before the setup time. So this does not violate anything. It violates it. We'll actually see an example of this right now. So yeah, that's a great question. So does this violate something? Yes? No? Yeah, right here, right? So this is an example of an input that does violate timing conventions. And right here, it violates the setup time convention, because we have a low value. And so theoretically, it should stay low all the way to when the hold time is over. But here we can see it changes in the middle. And that's not good. So that violates setup time or setup time timing convention. And so even though this like kind of dropping to before is okay, this still means that whatever is being written to the register and like read from the output here, it'll be undetermined, because even if it's written correctly by some miracle, we can't guarantee that it's correct. So we'll see how to write this on the graph in a second. So it cannot, right? Because it can't change between here, this line and then this line. Yes. Mhm. So then we have this. How do we feel about this? Yes, violate. No, not violate. Not sure. Yeah. Yeah, so we're not violating hold time here, right? Because hold time is between the rising clock edge and the like where the hold time is, so how much after it is. So right here it stays stable, but we violate setup time, which is in between the start of the setup time to the rising clock edge. So we see that it changes in between there. So it doesn't violate hold time necessarily for this particular register, but it does violate setup time. And then we have this last input. How do we feel about this? Yes, it violates. No, it does not violate. Meh. Yeah, so I think from all your expressions, kind of like I have no idea, because it looks very questionable. And yes, that's the point of this. So this is like something that you probably won't see because it's so variable. Like it could violate it, could possibly not violate, because in real life it's more of like a slight slope instead of just like an up and down. So in reality, like if you have something like this, it's probably going to veer on the side of like, oh, this is going to error, but you won't be shown something like this on a midterm or an exam. Okay, how do we feel so far? Okay, I see some slightly turning more up, so that's great. We're gonna go to the equations, and then we're gonna go through some examples. Oh, yes, also, I forgot to mention this, but this is how you show a value is not determined or it's undefined, because we don't know what the behavior is. So you just kind of like draw both lines and then like slash it out for that particular set. So I'll show you an example of how to do that when it's in the middle of the circuit in a bit. Unfortunately, I couldn't fit it on here. Okay, so Bernie mentioned critical path earlier. So that is the longest delay between two state elements. So this is between, say, register, register, memory to register, etc. And it looks something like this. So we might have register 1 and then register 2, and in between we have a bunch of combinatorial logic. So how we want to calculate the critical path is we want to take the clock to Q, and then we're going to add the longest clock to combinatorial logic delay from inside this pink section, and then we want to add the setup time. So these colors correspond to which components of the circuit that we're getting the times from. So the clock to Q comes from register 1, the setup time comes from register 2, and the longest combinatorial delay comes from the maximum of the sum of all in series combinatorial delays in here. So that's a lot of words. Basically what it means is look at every path that has in series kind of logic gates, add them together and see where the longest one is. And the reason is because we want to make sure that the clock cycle is giving the longest path a time to finish before we kind of hit the next clock cycle. Okay, so the reason that we have this is because, okay, well, why do we have clock to Q in the first one, setup time in the second one, and why don't we have the hold time? Any thoughts as to why? Yeah. Mhm. 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 Yeah, so you're pretty much almost all the way there. Did you have a comment or a question?
I was gonna say, is it because like where we're counting from is just leaving register 1 to entering, so that's why we don't have to worry about the whole time?
Yeah, so you guys are both right. So with the whole time, because we always know that it's going to be less than or equal to the clock to Q, we don't have to factor it in here because it's going to be the longest possible, right? So even if the yeah, so the whole time is less than the clock to Q portion. So I think what was mentioned was exactly correct because we want to make sure that we're able to actually sample the output from the register because that's what's going to be the input to the combinatorial logic portion. So there might be like another input over here, but this is the one that we care about because this is our state element. So remember when we're timing things, a clock cycle is going from rising edge to rising edge. So if we go, yeah, or I was going to go back to the previous one, but that was a couple. Let me see. So, excuse. So yeah, if we go to this previous one, a clock cycle is from this rising edge to this rising edge. And so that also means that like when we were talking about, oh, things being written or things being calculated, the next action is going to happen when the next kind of rising clock cycle happens. So we want to make sure that everything kind of bracketed in between is counted when we're talking about our clock cycle. So that's why, oops, that's why when we go over here, we want the clock to Q because it's from the first rising clock edge to when the output is actually recognized. And then we want the maximum delay in the middle so that the values get time to travel. And then we want to make sure, like he said, it remains consistent during the setup time before the next rising clock edge. So when these kind of are all combined together, we get our minimum clock period or our longest possible path. And so you notice that these two are equal, and having a minimum clock period means that this is the shortest possible clock period, so the shortest rising edge to rising edge that we can have that can ensure that this circuit stays stable. Otherwise, we'll wind up with a bunch of undefined values because certain things might be overwritten, we might be going too fast, and it won't give values enough time to actually write into the registers. Does that kind of make sense? Okay. So then corresponding, we have our maximum clock frequency. So clock frequency is done in hertz or more likely gigahertz. Minimum clock period is usually in nanoseconds. And so I forgot to write the G in front of that, but nanoseconds and gigahertz correspond to each other, and that's equal. The maximum clock frequency is 1 divided by the minimum clock period, and this is just in a particular second or in a period of time, how many times does the clock cycle? And so it's just 1 over the critical path, 1 over the minimum clock period. It's the same thing. Yeah. It is. It is, yes. So yeah, I would go with yeah, course material. Yeah, but we always call it the longest combinatorial logic and not the critical path, because critical path is the whole thing. Yeah. So I'll let CSM know about that. But yeah, so now that we have that, we have one more equation that's kind of important. So this one is like basically the same thing as the one that we had before, but the other important one is we want to know what our maximum hold time is. So the reason for this is because if we have too long of a hold time, we can violate other timing conventions as well. Because, for example, if we have too long of a hold time, then it might not guarantee that certain things are outputted, or that say clock to queue is less than that, or we might already have started the next cycle before the hold time is actually over. So effectively, if it goes too long, it can kind of start to get onto, it can start like encroaching onto the next setup time. And so then that'll cause kind of like instability of the flip-flops. So to calculate that is, well, imagine if you have the value changing right before when it was written, then that's not going to be very good. So if we don't calculate what the shortest path is, then something might be written and we already we say, oh no, you have to hold for longer. So if we have a really, really short path in comparison to a really, really long one, the hold time is basically saying, okay, I need a guarantee that the value won't change before the shortest path is done. Because if it's not done before then it might change, or sorry, if it's done before our hold time, then the value might change from the last kind of value, and that won't be good because then it violates our hold time. So we want to make sure that it balances between not too long and then not too short. So yeah. Yes. Yeah. Yeah. So once you have the shortest combinatorial logic, during the setup time, it should stay because it's already been counted into the clock cycle. So there will be no other values kind of traveling back to like change that value. Okay, so we have about 20 or 34 minutes left. So let's go into some examples instead. Let me stop screen sharing here. And I also realize it means I have to figure out what to share from my laptop. Hold on. Okay. Airtime. Yes. The max clock period basically would result, there is no limit on that aside from like the fact that you probably don't want a system that runs really, really slowly, because the minimum clock period is like you can't go faster than that, otherwise it'll cause instability. You won't have a maximum clock period because, well, you could just keep going longer and longer and it won't really change anything. It'll just mean that like all the values are idly waiting for the next kind of change in value. Okay, so we're going to take a look at question 4 on the worksheet. So we have a lot of text right here. You can read it on your own time if you feel like it's kind of going through some of the concepts that we talked about in the slides. The more interesting part is questions 4 and then, or yeah, just question the rest of the practice questions overall. I think we should have time to go through all 3 of these. But let's take a look at them. Do we want to walk through maybe doing one together and then, okay, I'm getting immediate yeses. So yeah, let's go through 4.1 part 1 together. So when we're looking at one of these questions, what we want to notice first is, okay, what kind of delays do we have and where are they? So we have, okay, the clock period. So rising edge to rising edge, it's 8 picoseconds. Is the highlight noticeable up there or should we make it darker? Yeah, I'm gonna make it a little bit darker because it's kind of hard to see. Is that better? Yeah, there we go. Okay. So yeah, the rising clock edge to rising clock edge is 8 picoseconds. So we know that from here to here, it's going to be 8 picoseconds. Notice that we don't care about this stuff over here because it's before the first rising clock edge. And so we consider that to be insignificant. So, okay, the next part is for every register, clock to Q delay is 2 picoseconds. The setup time is 4 picoseconds and hold time is 2 picoseconds. NOT gates have a propagation delay of 2 seconds. So this is important because first and foremost, almost all of the hardware that you should have, or at least in exam questions, homework questions, should have the same kind of delays overall or the same timing conventions. And the reason is because, well, when everything's kind of in one circuit, you want it to kind of behave similarly. In real life, I'm sure, again, there's an exception, but we will just not consider that for now. So now that we have that, we want to make sure that we have the actual inputs and outputs that we care about. So right here we can see, okay, we have a clock cycle that corresponds to this. So we notice that the clock signal comes out of here. It goes into the clock kind of input of register 1, of register 2, and of register 3. So this is what I was talking about earlier, is one signal can kind of split off into 1, and then 2, and then 3 different ways, right? So we're using the same clock signal on all of the different registers. So that's good. And then we have our input right here. So I'm going to use blue for that. So our input here starts out at a 0, which makes sense because our value here is low. And we can see that it gets only fed into the data of the first register. So that's important because then when we look at the second and third registers, we can see that the input is the output of the previous register. So looking like that. So it's dependent on the previous register. So which also means if the previous register messes up, it's going to affect the rest of our circuit. The last thing to notice is we're trying to kind of read or sample the value at different positions. Sorry about the flickering. I think like the connection is funky. So for S0, we can see that it gets sampled right here, which is directly the output of the first register. And that's also coincidentally what's going to be fed into the second register. So we know that S0 and this value are the same. Similarly, S1 is going to be sampled from the output of the second register, and that's also what's going to be fed as the input to the third register. So these two values are going to be the same. And then we have our final output right here, which is our final signal. So kind of getting started, what we want to do is, or rather what I like to do is, I definitely didn't do this when I was a student because I thought it was like not necessary, and I tried to do it all in my head, and I would highly not recommend that. But what I would start out with is, okay, first marking out where the different lines lie. So let's first start with the clock period. So we know that the clock period is going to be rising edge to rising edge. So we know between here and here, it's going to be 8 picoseconds, similarly with right here. And it does take a little bit of time to kind of properly diagram out everything, but it does make drawing out the lines and where they kind of fall a lot easier later down the line. So we have our clock cycle now. Now we want to, okay, so we're going to label that as being green. And then our clock to Q delay is 2 picoseconds. And remind me what the clock to Q delay is and where maybe it should fall. Yeah, so where would I draw this blue line? Yeah, so would it be like right here? Yeah, so maybe right here, right? Yeah, okay. So yeah, so this is again one of those things where you're kind of like guessing a little bit because we know that the clock is regular, so it's not going to go but like that because otherwise you're going to have arrhythmia and the system is not going to like it. So we can kind of assume that the falling clock edge and the rising clock edge sort of separate the clock cycle into two distinct or two equal parts. So here's that if we kind of go halfway in during the like high and then halfway during the low, it's going to be dividing things equally. So our let's see. Yeah, so the 8 picoseconds is one clock cycle, right? And clock cycles are from rising edge to rising edge. So yeah, this is 8 picoseconds. Yeah. But yeah, so that's a really easy mistake to make. So I'm glad you brought it up. So let's mark out the clock to Q delay for the rest of the cycle. So we have our very colorful lines right here. Our paper's gonna, or our screen's gonna kind of look like confetti in a little bit. Okay, so now that we have that, the next important thing is, okay, we have our setup time, and that's gonna be 4 picoseconds. So where's that gonna fall? So where's the first line going to be? But what? So over here or over here? Like just in terms of general. Before, so like over here. Okay, so yeah, so that's a great point that you bring up. So one of the things with this is you don't necessarily want to consider things that happen kind of before. Why is my could I adjust something? Sorry, give me one moment. Yeah, so one of the things with this is we want to make sure why is my screen stuck sometimes? Hello? Okay, so yeah, one of the things that we want to make sure is we don't want to necessarily calculate the values before the first clock edge. So yeah, like sure, theoretically, like our setup time over here would be like 4 picoseconds, but we don't really want to think about that because we only care about things that come after our first rising clock edge. So in theory, like our setup time would fall, the first setup time that we care about would fall somewhere along here. Yeah. Check difficulties. So we have this, and you can see like things are starting to get like very colorful and very kind of like very quickly. I'm gonna erase this just for space. And then our last one is 2 picoseconds for the hold time. So which line does that correspond to? Or do we need to draw a new line? Yeah, so it's going to be right here. So just to know, hold time is not always going to be equal to that. And if you have like slightly more complex circuit, it might not be that way. So right here, we can we know that this is going to be clock to Q. I'm just going to call it C to Q. But it's also going to be hold, and that's not always going to be the case. So sometimes we'll have to draw an extra line. Yeah, so again, remember, look, our hold time can't be greater than our clock to Q. So it would have to be less than 2 or less than or equal to 2. Yeah. Yeah. Yeah, so the pink one or the red one.
Yeah.
Yeah, so our setup time is 4 picoseconds, and that happens for 4 picoseconds before the rising clock edge. And so like in theory, if we wanted to like draw it right here as our first setup time, that would make sense. But because we don't know what happens with the inputs before then, it could like be all junky. We don't know if it's correct. We don't actually care about the stuff that happens before our first rising edge. So that's why we didn't draw one right here. So instead, our first one is going to be before our next rising clock edge. So that's why this is 4 picoseconds before then. Yeah, great question. Okay.
Like the falling edge, that's just like.
Yeah, yeah. So like, yeah, if our hold setup time were 3 picoseconds, then like we would just like shift this slightly, like maybe here. So yeah, it's just a coincidence. It's on the falling clock edge. Okay, so we're gonna move on to now drawing the outputs. So the outputs or what's being sampled here is almost always going to be in the order of when values are going to be being read from the register itself or from the circuit itself. So we can see that S1 comes first. So we know that the input that it's trying to read is directly from the input over here, and so that way we can follow the change in input right here. So kind of zooming in a little bit. Okay, so let's draw this with blue. Okay, so when we first start out, what kind of value do we have? Do we have low? Do we have high? Do we have not sure? So like right here. I heard some, sorry. Yeah, so we don't know what it is. And the reason for that is because, well, we only know what it is after our first rising clock edge. And right here, Our first rising clock edge is right here, and our input, what we care about, is only going to like be quote unquote valid by the time that we hit or by the time that we hit this kind of hold time right here. So for the first part, okay, we're not going to know anything until our first time right here. So this is going to be marked as not sure. And then so because this is going to be read as a low value, by the time the hold time is over, we're theoretically going to be able to sample. And so we'll have something that looks like this. And so we'll have a low value that goes all the way until the next kind of hold time. And then so now we have to look at what the input was during the setup to hold time over here. So during the setup time and hold time right here, the value is considered to be low, right? Because it hasn't changed. This part hasn't changed yet. So that means our value continues to be low all the way until the next hold time. And so now at the next hold time, we want to see, okay, during this kind of setup and hold time cycle, where is our value? Where is our value right here? What do we think this next sector is going to be? So this next sector that we're reading. So it does change, right? So we see it going from, it's a high right here, but then it does change right here, and that changes before the hold time. So how does that affect our output? Yeah, so we don't know what it is, right? Because it could be correct, it could not be correct, we just don't know. So how we're going to mark this as just in this section, we're going to mark it as a kind of a rectangle of not sure. And so we just continue onwards. Okay, so we want to know this next section. So between this next blue to this next blue line. And so what we want to look at is, okay, during this setup and hold time, what are we looking at? So during this whole time, we have a high value and it continues to be a high value. So therefore, in our next sector here, our output is going to be read as high. So we can see, like, even though there was a period of uncertainty in the middle, if the signal corrects itself, so if the input to the register corrects itself, then our output is going to be corrected as well, and we'll be able to read from it again. And so now we have one final stretch that we're looking at. So we're looking at this kind of setup time to hold time, and we can see that it stays high during this period. So we're going to stay high all the way to the end right here. And then in our final section, we have this setup to hold time, and we can see that it falls. And so now for our final portion off the paper, it's going to be a low signal. Right. So we're talking about let me see. We're talking about right here, right? Yeah. So we can see that between the pink and like blue lines, or oops, I think, oh wait, sorry, I drew the wrong one. It should be right here. There we go. So this was the issue right here, because between the pink line to the green line is the setup time, the green line to the blue line is the hold time, and we can see that it violated the setup time requirement. Yeah, so it's because it's between the red and the green line. Yeah, so this is setup. Remember, this is hold / clock to Q. And so that's why we're able to read from it as well, because the hold and clock to Q time are the same. Yeah. Mm-hmm. Mm-hmm. Yeah, so you can see that like kind of there's like a slight delay because it's reading from the previous clock to Q. Okay, now it gets registered in output. We're gonna keep producing the output until the next kind of section. So that's why like you can see like there's a slight delay there from the actual input. Mm-hmm. Are there any questions for S0? Okay, let's move to S1. This gets a little bit more interesting because our input here is now not the official input, but rather the output from register 1. So let's see how that affects things. I'm going to use an orange right here just because colors. But for the first part, okay. Well, for the first one, what we cared about was, let's see, the first kind of clock cycle right here. And that was kind of a low value right here. So we cared about that section. So now what we want to know is, okay, we're looking at S0 as our official input, right? So now we want to be able to tell from the first time that it's valid, we want to be able to read from there. So the first time it's valid is going to be in this section, right? Because right here, in the first kind of part, it's still considered to be uncertain. So we don't know the value right there. So we can only actually be able to read our value starting from maybe right here. So all the way before that, what does that mean for our value over here? Unknown, right? So we're going to have a slightly longer kind of scratched out section. And then so our first value that we're reading is from S0, and during that clock cycle, we can see that it's a low value. So we're going to persist until the next blue line. And now we can see, okay, well, our next section, what's that value going to be? So our next value we're reading is from the next red to blue line. And so that's this section. And we can see that it continues to stay low. So this next stretch is going to be low. We're going to continue on to the next portion. The next portion that we're reading from is actually this portion. So what does that mean for our output S1? We don't know the signal coming in. So do we know anything about the signal coming out? Right, so we don't know anything about it. So that means that this section is now also going to be kind of scratched out. So you can see that like things kind of get pushed back a little bit. Sorry about the flashing, it's really distracting. I don't know why it exists. But yeah, we can see that kind of the scratched out or uncertain portion got pushed back one clock cycle, right? And so the reason for that is because when we look at our official kind of diagram, we don't know anything about what the input does until one extra clock cycle from the previous one, because it has to go through this first one first before it even reaches our second one. So we have already an offset of one clock cycle because of the first register. Are there any questions about that? Okay, so then if we move to our final kind of set of inputs, so our next one is going to be over here. So that's going to give us a high value. So our final stretch, a full stretch right here is going to be a high. And so our last bit kind of over here, that's not a full clock cycle for the output, is also going to remain high because it remained high during the output there. So we can see that the output is going to remain high off the paper. So if we kind of take a pull back and look at this, we can see that generally this kind of pattern exists. Let me make it, let's see what color, let's make it purple. So we can see that this we had like a, okay, uncertain value, and then we had a low, low, uncertain, and then high, high. And we can see that kind of persists right here. We have uncertain, low, low, uncertain, high, high. It's just offset by kind of one clock cycle, right? And that's the result of kind of reading the output of the first register to be able to use in the second one. So it's always going to be offset by one clock cycle. So following that, we're going to have our final output that we're actually going to be reading. So our final out. And so this one, I'm going to let y'all take the lead a little bit. So let's use, what do we use? Purple. Let's use purple. Okay. So between which lines will we have our first valid signal for the output? Oh, sorry. We're not looking at this right now. We're looking at the this out here. Yeah. Yeah, no worries. So yeah, so the third green line. Yes, okay. So yeah, so that's going to be our kind of first valid clock cycle. So remember, we only read the output when it comes to the blue line because that's clock to Q. So we would start somewhere over here, right? So that means for the first kind of 3 clock cycles right here. So 1, 2, 3, our input is going to be what? yeah, unknown or output is going to be unknown. Yeah. So we're going to have scratched out for all 3 of these sections. And we can see now it's 3 times as long as the first one. And so what's our next signal going to be? Low or high? Low, yes. And it's low because, okay, we're reading from this setup to this hold time. And then our next signal is going to be, so in this section, what is it going to be? Unknown, I'm hearing some numbers. Why is it unknown? So this is what I'm hearing. Huh? So yeah, we do eventually sample from it. Yeah, because we're not sampling from S0 anymore. We're sampling from S1. So yeah, so we would be reading from the next kind of signal. So undo, undo, undo. So we would be sampling from this section instead. So it would be staying low, but yes, you all are right. For the next section, when we sample from this section, that's going to be unknown for the next component. So that's going to be unknown right here. And then for our final part, what's our signal going to be? High, yes. So it's going to be high because now we're sampling from this next clock cycle. Okay, so this is what our final results are going to look like. It'll probably not have as many circles and stuff. That's just used for diagramming purposes. But are there any questions how we got here? Yeah?
I'm confused because we have 2 inputs going into the third.
Where's the where's the second input?
You have the one coming from S1, and then you have the one coming like straight from the clock.
Oh, right here. Yeah, so this second signal right here. So yeah, that's a great point. So this second one isn't considered a data signal. It's considered a clock signal, and that just helps make sure that like we're actually following. So if we didn't have that clock time, then none of this would be valid because we're no longer following timing conventions. So we don't have a clock to obey. So we wouldn't be able to read or write anything.
So going into the R process. Right?
Yes. Or sorry, R is I think depicting register actually. The clocks, do you see like this little triangle? So
Yeah.
that's what I was talking about earlier with state elements. You'll always see a little triangle somewhere in there. Yeah. So, and that's indicative of where the clock signal is going into. Okay, so we have about 9 minutes left. I think. So 4.3 is a different kind of question. I'm gonna give everyone, so that did take a little bit of time, especially talking through everything. I'm gonna give everyone maybe like 6 minutes to work through the second diagram just to see how far you can get, and then we can go through it a little bit and see how it goes. So something to notice for this one is like earlier we had the same clock signal go to all 3 of the registers. The thing to pay attention to is here is we have a not going on right here. And the not right here is kind of saying, okay, well, I'm actually going to invert your signal. So the inverting of the signal, so the first register obeys the regular clock signal. The second register obeys an inverted clock signal. So when the first clock signal is a 0 or low, the second one is going to be a 1 and vice versa. So the first one is a 1, the second one is going to be a 0. So we can see that the rising clock edge and is offset. So otherwise, all the timing conventions obey itself. So register 1, the A input, and then the R1 output, that's going to obey the clock, like the official like clock signal. And then R2, because it comes from register 2, it obeys the not clock signal. So give everyone a couple of minutes to work on it, and then we'll go over things. Okay, so I'm just going to walk through this, and hopefully it's enough time. But something to note here is that we have the inverted clock cycle. So if we were just to have an instantaneous inversion, well, we would have, so I'm going to make, this is the bad one. So we would have something along the lines of like high and then to low and then to high and then to low right here, right? Because that would be the natural inversion, but we can see that that doesn't correspond to right here. And instead we can see that like things are shifted over by a certain amount. Things are shifted over by this amount in terms of where kind of things are. And that reason is because we have the 2-second inverter delay right here. So remember we have NOT gates have a 2 picosecond propagation delay. And so that affects what kind of signal comes out to be fed into the clock. So that's why the clock kind of looks like this, and it's not a perfect one-to-one kind of correspondence right there. So I'm going to erase the wrong clock right here. But a good way to look at this when we, especially if we have multiple clock signals, is first to just like look at one kind of set of lines and then look at another set of lines. So I'm going to, right here, I'm going to use only one color because otherwise it'll get really messy really quickly. But remember earlier, we have our kind of clock period. So I'm going to use dashes for that. Sorry, I'll get it out of here in a second. Okay. So we have our dashes for that. I'm not going to go all the way to the end just because time. And then remember we have our setup time, which is going to be 4 picoseconds. So I'm going to use dots right here. So that's going to be our setup time right here. And then we have our hold and clock to Q time, which is the same. And that's going to fall somewhere in between here, remember, because it's 2 picoseconds. So I'm going to make a squiggly right here for that. So this is like, if you don't have colored pens on an exam, this is something that you could probably do. And so when we look at the output right here, R1 is coming out from only register 1. And so when we kind of take a look at this, okay, well, if we want to calculate it, we know that the initial part right here, we can see that there is some kind of input, but we only really want to pay attention to when the first kind of clock cycle hits. So what we want to do is, okay, well, first clock cycle is starting around right here. So we only want to start looking in this kind of next section, right? So this next section for the clock to Q, or yeah, is going to be, sorry, setup time is over here somewhere. It's going to be this section. So starting from this set of hold and clock to Q time, we're going to have a high signal right here. But before that, we're going to have uncertain. So we're going to scratch that out. And then so looking at the next section, so the dots to the squiggly, we have a low value. So that's going to convert to low. And that's going to go into our next dash line. And then we have, okay, our next section, which is going to be high right here. And that's going to convert back to high for however long. So basically that section kind of stays the same. And then if we try to look at our second one, this is where you might want to switch to a pen or something like that. We can see that it's not going to follow exactly what we had as the previous one, because we know now that our clock cycle is going to look different. So now the dashes are going to fall right here instead. Because we're following a different kind of clock signal now, not a different clock signal. And so when we have this, okay, now we need to mark in where our hold time is going to be. So our hold time and clock to Q time is going to be 2 picoseconds afterwards. And so that's going to actually coincidentally kind of fall where our, clock cycle time is going to be. So it kind of corresponds in terms of lines, but we're just going to use a different color for that. And then our final one is the setup time, and that's going to be a squiggly, which is going to fall actually right here, which is exactly where we had it before. And so we're going to follow the inputs here. So we want to make sure that we have the inputs going from the start of our input to the clock cycle. And so right here, we can tell that it's this next section is going to be not determined. So that's going to be our all the way up to our hold time. And then we just continue kind of the signal from there. Sorry, that was a little bit rushed. I don't want to take up too much of the lab people's time. So we're going to end it right here. But if you have any questions, feel free to talk to me afterwards. There's also going to be a review session tonight, 7 to 9 in SOTA 405, and also online. The room will be posted on the corresponding post. And we're going to be going through old exam questions. So yeah, thanks for stopping by, everyone. And yeah, good luck on the midterm. Yes, it is. Yes.